Good morning. This is Anand Srivatsan. Today's class will be on artificial networks. So today's basically the neural networks was thought of as a outcome of how the computers guys and other people understood as how neurons works, the biological neuron that are there in our body, how they get stimulated and what are the neuron, how do they actually work. Based on that, the neural networks have been um, thought of as an inspiration. So if you look at it, the here is the one which actually says that this whole thing is the cell body, and the one which the information that actually fluid like thing is the soma, and the cell body which has the nucleus, and these are which looks like tentacles are the dendrites. And the one once these are all attached to some other s- similar to like this, they are attached to the synapses of other neurons, and they get attached to this one as a input to this particular neuron, as an input to this one from some other neuron, as an input to some other neuron, as an input to from some other neuron. So basically, once the neuron, the nucleus gets some certain stimulus of it, so after some threshold, an output flows to the next to this particular synapse as an output, and this actually goes and which is attached to another neuron, gets the stimulus. So if you look at it, this whole thing of the idea behind how the biological neuron works, based on that, neurons in artificial intelligence have been thought of. So looking at this as an inspiration, they started to work on how it should be um, activated, how what is the threshold that needs to be thought of. So this was the inspiration for the artificial intelligence scientists to look into. Now, what is the relationship between biological and artificial network? So biologically, there is this soma, and there is, that means the one particular the the bulged neuron which had the nucleus, that's the soma. Here in the artificial world, it's called node. Dendrites, from which the input comes. Axon is the output to the next dendrite, to the next soma or the next neuron. Synapse, that means some kind of weightage that stimulus stimuli the dendrites to think whether it's being hurt or not hurt, and what is the weight of that particular input. Synapse actually tells you. Slow, biologically they say it is slow, but artificially fast. Many neurons, 10 to the power of 9, few neurons, a dozen to 100 of thousands. Okay, not much, but these are the information that neurons, artificially you need less neurons to come out to a particular cells. Now in the similar token, now let's look at how processing information in an artificial network happens. That means there are certain processing units which does the part of actually looking at the inputs and the weights. What are the weights? What are inputs? First of all, the inputs are the parameters, are certain coefficients and parameters that you think makes sense, that are parameters that make sense to whether I should, what is the weightage, the input that I need to consider. For example, let's take a loan. A bank whether they want to give you loan or not. So first of all, they need to look at whether are you having previous credit history. Fine, okay, credit history. Then then they look at whether the particular what is the age, what is your income. So these are the inputs. Okay, now this, if these x1, x2, x3 to xn are inputs, to which input should I give you enough weightage such that I can consider it for me to give you loan. That's how the bank looks at. It's not whether you're young or whether you are, can you pay back the money that you are, can you pay back the money. So they look at certain parameters as to, and out of those parameters, how much weightage should I give it to each of them. So these inputs and weights are related to that. So if I look at it, x1 is the input. What weightage should I consider it on the input such that when I add all of them, it should give me some kind of a, this processing unit does some kind of a check. Okay, it adds up all these x1s and weightages and see whether it adds up something. Now this processing unit also does something and it gives it the next, this is the check. Okay, this output comes in and here it comes and checks whether I should, whether it should be considered to which particular output it is giving me or not. So this, that y actually tells me, here is where the function which actually looks at whether I should consider yes or no. If it is a binary output, if it is yes or no, there are y1 to yn I have put, but there could be chances that, let's say this max of something is, this function could be max of something, okay, or it could be yes or no. Okay, it could be an yes or no function. Now how would I say that it is yes or no? Certain point times you would think that it is just crossing certain level and it should be considered or not. If it is crossing a particular threshold, yeah, then I would consider this to be yes. If it is not crossing the threshold, I will not consider that as a yes. It will be zero, no. So this is how the processing unit works. So let me look at it. Let me show you, put it back into it. So here is the input which comes in, and here is the weightage. Okay, x1, what is the weightage, and x2, what is the weightage. Let's say this is y. Okay, this y is equal to sigma of x1 xi wi, where x is I is equal to, sorry, I is equal to 0 to n, or I is equal to 1 to n or something like that. So I consider all of it, then I consider, I get a y. Let's say I put a I'll give you an example, but let's understand this is how the artificial network works. So once I put this is a function. This function will tell me whether it should be yes or it should be a no. Okay, that's how this artificial network works. Next, so let's look at the elements of artificial network, composed of processing units organized in different ways to form the network structure. And it organized in the sense these processing units could be handled in different way. Let's look at certain graphs later, but let's understand the elements of artificial network. The basic processing unit is the neuron. Neuron in the sense here, the one which actually is the one considering this whole thing is neuron. Okay, from here to here, this is all neuron. The output is an output which comes out of this is the output. Okay, what comes into what is what is this neuron, what is the input x1, all these things are a neuron. That what you do over here is the neuron. Okay, that part is what is we are trying to understand. The basic processing unit is the neuron. The number of neurons are then organized into a network. Neurons can be organized in different ways. These various networks are referred as topologies. One of the popular approaches, feed forward or back propagation paradigm. We'll look at this later. I'll give you a scenario to that. The processing units of an artificial neural network are artificial neurons. Each neuron receives inputs, processes them, and delivers a single output. That output will determine, will go into a function which actually output function, which actually tells whether to which one yes or no is what is. The input can be a raw input or the output of another neuron or processing unit. The output can be the final result, 1 or 0. Okay. Now if you look at it, these are neuron networks with one hidden layer. Which is the hidden layer? This is the hidden layer. Okay. So the neurons, that means they are getting, each processing unit is getting some neurons, some inputs and weights. Okay, some inputs and weights. X1 going here, and y weight of that one. X2, some weight to it. Similarly, This x1 could be the same input to this one, x2 could be the same input to this one, x3 could be, right? Like you would have done digital system design, isn't it? You would have had ands and nors and other stuff, and you would have y is equal to some formula based on min terms and max terms, and that this is the similar, it is similar to that one. Okay, this output input weights and all coefficients, all these things, let's think of a system, digital system design. This processing unit does that part of it. Like this could be in our digital, in our electronic system, this could be our, it could be an and, it could be an or, okay, it could be an and or something like that, which gives you all these things, and it comes to another another unit like this. Okay, and the output of that, that's what is this y is. So if you look at it, these inputs, these weights all determined to come out to something, then this will decide whether to go to something, and that will finally will decide what is the output of this processing unit will be the output. Coming to that part, this final processing unit will do the final job of it. So we'll look at a lot of examples as to how to understand this. So network structure, the hidden layer is a layer of neurons that takes inputs from previous layers and converts those inputs into outputs for further processing. You just saw that hidden layer does that part. Okay? The hidden layer simply converts inputs into non-linear combinations and passes the transformed inputs to the output layer. The most common interpretation of the hidden layer is as a features extraction mechanism. That is the hidden layer. That is the hidden layer converts the original inputs in the problem into a higher level combination of such inputs. These are just notes. Okay, I'll send it to you. Don't worry. Each input corresponds to a single attribute. This is what it is. Single attribute. If there are three attributes such as age, income, and home ownership status to approve for a loan or not, several types of data such as text, pictures, and voice can also be used as inputs. So pre-processing may be needed to convert data into meaningful inputs from symbolic data to scale the data. That's what we do when we get a pixel, an image, we convert them. If it is a 28 by 28 pixel, we convert each pixel into an input that will go through each of the processing unit, and that converts into something else based on the weights that happens. How does the weights get created? How do they actually maximize or minimize? How do they adjust that weights to itself, and how the weights actually final weights are decided such that the information that comes out of the image is extracted appropriately. These all things makes a lot of sense when you look at some examples. The outputs of a network contain solution to a problem. So it could be 1 or yes, or from 0 to 9, or anything, an image. All these things can be any of the outputs. The purpose of the network is to compute the output values. Connection weights. These weights express the relative strength of the input data that fed into the input processing unit. That's what I explained in the starting of the start. At the start, they express the relative importance of each input to a processing unit. Okay, and ultimately the output. Okay, the weights are crucial in that they store learned patterns of information. It is through repeated adjustment of weights of a network, that's how it learns. Okay, I'll show you one example. Good example, very good one. Okay, now let's look at summation function. Okay, now the summation function is, let's say this is the kth in one of the neuron, which is could be kth neuron. Okay, neuron x1 is coming in here with using this weight, and x2 is coming with some weight into the processing unit. This is a single neuron. Okay, now let's look at the outputs of each of the processing unit and their expressed equation. Okay, x1 and x2. Okay, it's going through through with some weightage, and x2 is coming. Okay, this should have been like this. X2 is coming not from weightage 1. Okay, all of them are weightage 1. So wait, think that this is I forgot to change this. So this is w1 1 1. This is 1 2. Okay, x2 has to come from here actually, sorry. Okay, should have come like this. Okay, x2, and this should have been the this should have been 1 2, and this should have been 1 1, so don't worry. Okay, now if that is the case, this would be 2 1. This is 2 1, this is 2 2. Okay, now if I look at it, now this y1 is equal to x1 w11 plus x2 w21, and x2 here y2 is equal to x1 x1 w21, and this is w2. Okay, this little bit weight is changed, but I think you understood what I am trying to do here. And this y3 is equal to x2 into w23. Okay, this one. If this is the case, this is how we need to actually adjust the equations are being worked out. Okay, this is the equations are being worked out, but once this equation comes out of it, we start with the random w numbers. Okay, with some random w numbers, and we run this n number of times to see whether the output comes out correctly or not. And if the outputs are differing from the actual desired output, actual outputs are not the same as the desired output, then we adjust the weights. How we adjust the weights? By epoching and sending back this desired output back to this. Okay, how the weight gets changed, all these things are a next process. I'll show it to you next. Okay, now transformation function, the summation function computes the internal simulation or activation level of the neuron. It either produces an output or not, depends on this activation level. Output can be linear or not linear. Okay, selection of the specific function affects the network operation. What kind of function should I be looking out? Based on that, it will tell me whether I need to have a particular which kind of activation function should I use to see that it actually works properly. Okay, now earlier when sigmoid function is an afterthought, but let's say look at it, you could have there could have been a step function that could have been used. For example, something is at some point somebody thought square function is a good one. Okay, at some point it will be a very good thing. So they thought, okay, at 0, at some point some threshold will happen, and it will actually go and say that this is where it activated, and that's how I get a 1. Okay, and this would be 0. Now the thing is, as long as x is equal to 0, it is 0, and even at some point of x is, let's say x is equal to 0 is 0, and x is equal to 1 is also 0. Now at what point should this become y is equal to 1 is at what point of x is equal to 1, should it be 0 or should it be at 0 or should it be 1 was a challenge. So they thought this step function is not a good one. So there should be some other way we should be able to differentiate between a certain point of x value and certain point of where it's supposed to be decided as a 1 or a 0. So then came the sigmoid function. Now how does the sigmoid function comes into existence? This is where they thought, okay, the sigmoid function is something like this, where as long as it is some certain things of something. Okay, as long as it is certain point of it, let it be still 0, and then it actually moves over and becomes things. Okay, it becomes 1. So if this is 1, okay, and if this is 0, and anything less than 0.5, okay, anything less than 0.5, let it be 0, and anything greater than 0.5, let it be 1. So this sigmoid function actually does a good job of differentiating whether it's supposed to be a 0 or a 1, as long as that y function, which y is equal to, that y is equal to 1 by 1 plus e to the power of minus y. But what is my e? This is a function which actually gives me a value between 0 to 1, but that is good. But what is this? What, how do I decide this y? This y is equal to, this y is equal to, our sigma is equal to, I is equal to 1 to n x I wi. If you look at this, whatever comes out of this as an output, that is the y that you will use here to get this threshold function output. Okay, so if you look at this, let's look at an example next one. With this sigmoid function, the output levels to reasonable values between 0 and 1. Without such transformation, the output would reach a very large number, because when y is equal to something, okay, y is equal to something, I'll show you an example. Okay, I'll show, the example shows that when w1 x1, w2 x2, w2 3 x2, let there are some 10 inputs, the y value will be very high. So how would you say which one actually made a difference as to whether it was, which one is a good one? Which should I consider something, the output, which one should I consider as a threshold? That's a very difficult part. So they made this, the function, the sigmoid function, actually transformation function, helps us to decide to be 0 or 1. Without such thing, it could not have happened. Threshold value is used instead of a transformation. This threshold value is a stop point for neurons output to go to the next neuron or not. If it is the output, if in this function, if the output value is greater than 0.5, then it triggers to the next neuron, or else it does not trigger. Okay. Now, usually hidden layers are of 3 layers typically. In our usual this thing, 3 layers are good enough. But the more the hidden layers, the more the computation required, that which is not needed. So that means after certain layers, you are only actually adding more neurons to see whether it actually merges to a particular, and your accuracy increases to a greater than 0.9%, 95% or something like that. But 3 neurons, or maybe typically 3 neurons, will usually reach to their maximum accuracy values. Okay. Now let's take that neural network architecture which I was trying to tell you. Now if you look at it, x1 is equal to 3 and its weight is equal to 0.4. x2 is equal to 2, its weight is equal to 0.6. x3 is equal to 1, its weight is equal to 0.2. Now if I consider y is equal to sigma of x1 w1, x1 into w1, x2 into w2, x3 into w2, if you add up all that, which comes to like this, and which is 0.2, 0.6. And if I put that minus 2.6 here, okay, 1 plus e to the power of minus 2.6, since inverse of it, all I would get is 3. Now looking at this, if the sigmoid function is something like, if the sigmoid function is something like this, that means my 0.93 is coming to, my function is like this, my 0.93 is this. Okay, that means anything above this is 1, right? Anything about this is 1. Okay, so if I get something like this, the y value is 0.93 here. If this is 1, okay, 0.93 is somewhere here. That means my sigmoid function is something like this, which actually is here. That means my point value, which is 1, so this could be, this is actually 1. So this is how the processing unit actually works. This is what I thought of explaining to you, and hopefully you understood something out of it. Now the next part of it is related to how the neurons are, which of the different learning algorithms, supervised algorithms, and how do we actually, in the next class I will actually take one example which actually explains you related to related to the a particular I might also show you how I did it through a, if at all I write that code, I'll show you the code also how it actually works using x1 x2 w1 w2, a random w1 w2 and a learning rate, how actually would, how the weights are decided at the end of it. Okay, so next class I will explain about the truth tables, R diagram and AND diagram and XOR diagrams, and how those guys, those exactly are how they are actually works, and how the equation turns out to be, and how it will be actually, um, how it actually works to the, to give an equation, and how you will determine that particular part of how you determine the weights of it. So how the thresholds are determined, all these things you will come to know through the next classes. Okay, and I'll one more class I will do after that. Next week anyway is exam week, so I will not do that right now. Okay.
Sir, one question.